Okay, so for today, basically, I just wanted to look at, I did hear about the XD drama, pure insanity. Maybe I can pull that up and talk about that first. There's always this is always a possibility with open source, right? So yeah, the internet is going wild about it. This thing, right? So apparently there was a backdoor, like somebody was playing the super long game of basically getting credibility within the community for the XZ project, which is maintained by a single developer. Basically this user, GT75, G10, or however you pronounce that, started making commits back in 2021, and then apparently they were also submitting patches via the XZ mailing list, and then another user, probably the same actor or whatever, was pushing for merges, and then basically that user was never seen again. And then they go over some mental health stuff with the maintainer. Obviously there's a lot of open source maintainers who are not paid for their work, and it's a ton of work, especially on a project that's used in basically every Unix operating system on the planet. And yeah, I'm not too familiar with all the technical details, but apparently the implication is that there's effectively somebody who's backdoored this project, and it's included in a whole bunch of different projects. Specifically, SSH was the main concern. So it was found by Andres Frund on Mastodon. And he basically noticed it in an SSH instance. So the only funny thing is how this problem got caught. Someone noticed 500 milliseconds of unusual latency. Yeah, thank God. I wonder where this person works and where it was being targeted. Because they probably weren't doing this for mass exploitation, but all right. So I've been in the security industry for 12 odd years, and there's been an interesting development with respects to red team tooling. So this might sound like old man yells at cloud kind of thing, but there's been a lot of interesting developments in even recent years, like post-COVID, or even pre-COVID, kind of 2019. I remember going to DEF CON, and there was, I did a training at DEF CON for some malware analysis stuff. I was presenting the training, and one of my students said he was a malware developer, and that kind of caught me off guard because usually people don't call themselves that. I'm pretty sure he was a white hat, he was working for an actual company, but it was pretty interesting nonetheless. And then fast forward to recent years, where we have all these different C2 frameworks. So for example, some of the ones that I wanted to look at today are Havoc, which is written by this Spider person who's only 19 years old, which is very impressive. And then Sliver as well, which is developed by Moloch, Joe. I'd say Sliver is probably one of the most mature C2 frameworks that are currently in existence. But just to kind of give you a timeline, I thought it'd be fun to open up. I'm just going to open up Keynote. So talking early 2000s, whatever, when commercial security was just getting started and like formalized, and people were starting to actually care about security, there was really only closed source projects that companies were using for like penetration testing. Obviously, there was real malware that was being developed by malware authors and being distributed. But there was never really like the commercialization and the legitimization of malware development. And this is like my own perspective. You all might have had different experiences if you've been in security for a while, but kind of essentially how it started was, let me just get my shapes. So you had the Metasploit framework. You had projects like Backtrack Linux, which eventually turned into Kali, which is what we're going to be using today to use a bunch of this tooling, just because there's already existing tooling in place, and we can use what's already installed on Kali. Basically, it's a Linux distribution that can be used to do red teaming and penetration testing. But yeah, early on, it was kind of like these two. And with the Metasploit framework, so I'm sure most of you have heard of the Metasploit framework before, but if I open this up, Rapid7 acquired the Metasploit framework effectively, but initially it was an open source project developed by H.D. Moore, who's a very famous security researcher. Now he works on kind of an asset discovery project, which is high impact. So I think it's good that he went to that space. But Metasploit is essentially, let's see if I can pull up the GitHub. It's a project written in Ruby, and it's kind of a exploitation framework that can lead to post exploitation. So what the Metasploit project didn't really fill at this time, let's just say this is like kind of early 2000s, or sorry, late 2000s, early 2010s, was the post-exploitation facet of like penetration testing. And even at the time, like red teaming and all of these disciplines weren't really formalized and like referred to in industry as they are today. More often than not, there was very much penetration testers and network penetration testers who would use either their own built tooling, or they would use commercial remote administrator tools and post-exploitation and stuff like that. So in order to fill this gap, the Metasploit framework introduced what was called Meterpreter. So if I get an arrow here, we have kind of after 2010s or like early 2010s. I can't remember exactly when Meterpreter was introduced. I could probably search for it, but we had Meterpreter introduced to the Metasploit project. And then after that, we started to see some interesting things happen. So not only was Meterpreter very effective in post-exploitation activity, so how Meterpreter would effectively work is in a modular fashion to a bunch of these other projects that we're going to look at today. And it was written in C. It wasn't written in Ruby like the Metasploit framework. So I think you can actually even look at GitHub talk. I want the actual, oh, it's been archived, whatever. But basically, I don't know how they have the current source structure set up now, but you can go and look at all of the different code for the Meterpreter, payloads that Metasploit was generating on the fly. So how a lot of these frameworks usually work is they'll usually have some sort of like base application that they'll utilize to perform the initial loading of whatever base module you have. So for example, Meterpreter. And then they have a modular framework that allows them to load additional plugins or content. A bunch of different frameworks refer to these in different fashions, but that's why collectively they're called a framework, because they're made up of multiple modules and different types of functionality. So kind of after Meterpreter came around, this was still kind of like early 2010s, I would say. Then you had the introduction of like, let's say, and this is kind of when Kali came around too. I think Kali might have been before that, but basically it was just a rebrand of Backtrack. So this term red teaming is like all the way back from like the 1960s. But basically it's, it's kind of used in two facets in the industry now. It's kind of gotten used as like a commercial term that's used to sell the concept of red teaming to organizations that basically want a high-level adversary emulated within their environment. So with penetration testing, you had a lot of surface level and highly skilled attacks that were occurring, but they were usually very noisy. There wasn't any limitations, and a lot of these organizations wanted to test out their blue team, which was essentially the other side of this red team in the formalized definition, in order to assess whether or not their blue team would be able to catch a given adversary in their environment if they were compromised. So again, this is kind of like defense in depth stuff and security 101 stuff that I won't really go into too much. But what's significant about this is that this overall shift in the industry resulted in a bunch of different projects being created. So there's open source tooling that we're going to be looking at today, but there's also a whole bunch of different commercial tools that are available today. So like I'm sure you've heard of Cobalt Strike, which is now owned by this company called Fortra. And basically what this kind of tooling allows you to do is have red team operators purchase commercial tooling that they then employ within their red team engagements. So why that's significant is because you effectively have this feedback loop of red team operators making use of this type of software that's very much more stealthy and less likely to get picked up by blue team tooling. And then you had kind of this commercial feedback loop of red teams employing this functionality, security tools attempting to catch up with tools like Cobalt Strike. And then everything's kind of like rapidly progressed from there. So you have tools like Cobalt Strike, you have BRC4, like Brute Retell, which is another big C2 framework that's commercialized right now. You have, I don't know, we don't have to go through the list of different commercialized tooling, but these are all pretty interesting ones that you might see as a defender like in your environments. So that's kind of just a general background on kind of how we got to the place we are today. But what's really cool about these open source projects is it lets you gain insight into some techniques that red teamers are employing in the wild, and it makes it accessible to everyone to contribute to. So again, like I mentioned, Bishop Fox has the Sliver project, which is quite mature. It has, so if we look at the docs here, I think I already have it open. We have the Armory. Let me make this bigger for you guys. So the Armory is interesting in that I can just go to the GitHub, but it's effectively like external modules that can be added to the Sliver framework. and those can be adopted by red team operators on the fly, like during their engagements. So you might recognize things like Mimikatz that I just passed, hash dump, so dumping SAM hashes from memory on Windows. There's a few others that Sharphound, which is like Bloodhound stuff. So this is all like Active Directory propagation and enumeration stuff. SQL Recon. Yeah, okay, cool. I just want to make sure this was the right SQL Recon. So this is actually developed by a friend of mine, Sanjeev. So shout out to Sanj. So this is used for like post-exploitation SQL Recon stuff, and he works for X-Force Red. So he's actively contributing to this module that's included in Sliver. So what's cool about like these frameworks is essentially you have red team operators contributing to the base project, but then you also have these modules that are being actively developed by other red team operators, and then you kind of have this whole suite of tools that you can use throughout your engagements. So another project that I want to look at too, I haven't really done a ton of stuff with, is Havoc, as mentioned earlier. So you might recognize this user interface from an older tool, but effectively it provides like a nice GUI interface and like a quick start guide for very similar functionality to what I explained with red teaming stuff. But what is interesting from like a blue team perspective, like from my perspective, is that you have these types of frameworks being deployed in environments and being captured, and then we as like reverse engineers then need to analyze those commercial payloads in order to understand what they're doing, like extract their C2 addresses, etc. All right. So, and then another interesting development that's happened is folks have effectively become like full team, or not full time, but like maybe sometimes full time. But there's a lot of folks who have effectively become like full-time malware developers. So, and they'll refer to this as like MalDev. So like MalDev Academy is probably the most popular academy for learning how to do this stuff. Also think it's super cool. Spider's a part of MalDev Academy, so I didn't even know that. But yeah, this is probably an interesting development just because there's become like the overall adoption of like MalDevs now. So if we do like MalDev as a commercial practice, and I would say this probably occurred like, I don't know, let's just say 2020s. So like now you effectively have folks on red teams or at organizations who effectively do malware development full time, right? Or at least part of the time, but they do it for Sector 7 training too. Oh, yeah, cool. Malware development essentials. So yeah, so you see what I mean? Like we've kind of moved away from the initial wording and phrasing of like a lot of these projects used to say like for educational purposes only, or like they would essentially make sure that you weren't using these for malicious purposes. But now from like a commercial perspective, we've effectively moved into the realm of like, this is how you develop malware. So for me, just the wording and like the phrasing and like I often hear people now being like, I want to be a malware developer. Which whenever I hear that, it sounds like they're going to do it for malicious purposes, but whatever. It's just my old man ears, I guess. So yeah, do like Sector 7 and MalDev Academy. All right. So yeah, that's kind of the timeline, like super rough timeline from memory. Obviously, some of these are probably wrong, so let me know if let me see when Interpreter was introduced. So yeah, and then basically where we're at today is these open source frameworks that I wanted to look at. So what I've done is, so I've installed Sliver already, and it has like this nice user interface. This is actually a very similar interface to Metasploit, which I don't know if that's what they were going for, but and we can essentially use this to do everything related to the framework. So if we do like Armory, so there's Armory payloads I was talking about. We have different flags that we can provide. So we can do like Armory search. We'll just use like SQL as an example. Let's refresh the cache. So like SQL recall and like that payload I was looking at a line. So it's like really user friendly, right? And I can do like Armory install SQL recon, and then it's done. And then we can like actively use it. But if I actually want to generate like malware, essentially, is there clear? Oh, nice. I can use generate, and then we can specify a bunch of different things. So we have, one of the interesting, let's do that. We'll mess around with it because I think it's a cool idea. So they have what's called canary domains, and they'll embed like these plain text domain names in the payload that are not obfuscated. So if you were like a blue teamer, you ran strings on the payload, and then you contacted the provided canary domain, that can indicate to the red team operator that you've found that domain and that you're reversing their payload, essentially. So that was a cool idea. But we can do like, I think I have, okay, because I did this earlier. So if I do, so let's just do invoke stream, and then we'll do a canary domain -- canary test dot. I think that should work. And then we can do something like, I think HTTP, something like that. So now this is going to generate an implant. So you'll notice that with a lot of these red team frameworks, you have these malware payloads being referred to as implants, which is just like taken from other parts of the industry as well. So one thing that I should note about Sliver is that it's written in Golang. So the payloads are quite large. So if we go to implant, and we look at some of this source code, then this is all Golang. So I'm actually a big fan of Golang. I've been writing some of it over the years. I really want to write more of it because I feel like it's strongly typed, and there's actual real data types, and it's like very similar to C, but it's very friendly to read, and the learning curve isn't huge. So I'm pretty stoked that this project's written in Go. Okay, so we generated our malware here. And then if I look at this binary, then we can see that it's a PE32 plus GUI executable for Microsoft Windows. So the way that they're able to generate these is that they have minimum GNU for Windows, which is a compiler that can cross-compile to Microsoft Windows. Or they use that for some components of this. And Golang is also has the ability to cross-compile. So pretty cool. You can just like generate payloads on the fly and then give it options and whatever. So what I wanted to look at is actually what this looks like from like a blue team perspective. So you got like a Sliver payload. We can look at what that looks like. So let me open up my. So there's a whole bunch of different stuff to go over here. First and foremost, I'm going to use IDA just because they have better support for Golang than something like Binja. And here, as you can see already, as I mentioned, this is like, these binaries are massive. So if I go back to my terminal here, we do like du-h on invoke. It's like 17 megabytes, which is like bananas. So let's see if we can like find those domains I was talking about. Anyways, it doesn't really matter. But what does matter here is Golang effectively produces like a statically linked binary, which is massive, as you can see with 17 megabytes. So it makes reverse engineering it quite a bit more difficult. So if we go to our code here, they also have compile time obfuscation of all strings. So I'm curious as to how that's implemented at the code level and then what it looks like within the actual code. What I might do is actually produce a debug binary to start off with, just so we're not siphoning through, like, this is 22,000 functions, right? So this is gonna be a giant pain. So let's do that. But do you all have any questions? I know I just blabbed a whole bunch. Yeah, Matt Depp, yeah, it does help with certain AVs because they'll limit the overall size. Yeah, let's hop back into Sliver, and then we'll do generate again, but I think there's a debug flag, and then I'm really curious what kind of debug output it's going to provide. But hey Josh, just in tuned in, looks fun. Hey Everest, how's it going? RPC code unknown unique constraint failed. Build's name. I don't know what that means. Did it actually produce the implant? Probably not. Maybe it's because we already have a binary of that name. Okay, yeah, that was a problem. So maybe I should report that bug. So I wonder if this actually it must be unique. Okay. No, weird. Whatever. Let's one thing I do want to do is see what these look like in assembly line. So again, kind of like going through the scenario of you receiving one of these implant binaries as a analyst. I'm just gonna log in here. All right. So yeah, I'm really curious what this is gonna do. I'm also going to, it's big, so it might take a little bit longer to upload. But this is local, so it shouldn't take that long. But yeah, this is, for those of you who do not know, this is like a binary triage automation project that is freely available if you guys want to check it out too. All right, while that's running, let's keep taking a look at the code in IDA. And I'm also going to use go resum to recover some information, and I'll explain what that is as well. Okay, so yeah, as you can see, like IDA will pick up some certain name functions, but there's not a ton to go on. But what's nice about Golang is because it's effectively statically linked, you have a bunch of embedded function information most of the time that you can visualize here. And then you can see what libraries have effectively been statically linked against the binary. But what I'm seeing is if they've basically stripped all that with at least the technique that IDA is using. So yeah, there's a bunch of crypto libraries. compression libraries, kind of all stuff that would be important to include in a C2 framework. IO operation stuff, there's net stuff, and there's a bunch of operating system and regex stuff, whatever. So we don't have to look at all that, but basically what we want to figure out is what Golang code is associated with the implant functionality itself and what's been obfuscated at compile time. So maybe I'll open up the source code. Here's our little notes for today that I'm going to include at the end of stream, but let me clone this and then open it. Okay, so we have our results here. I'll just go through this real quick. As you can see, not a ton to go on in our little framework here. The repo is also pretty big, like hundreds of megs. All right, and then I'm going to open this with Visual Studio Code. Sorry about this. Okay, so one thing I will do is we're going to analyze that with GoReSim. So this is a really good project from Mandiant that essentially helps with analyzing Golang with IDA. And what you can do is actually provide a Golang binary, and then it'll extract a whole bunch of different metadata like function names, etc. And then you can apply that against a binary that you're reversing. So just because IDA doesn't have the ability to extract all the metadata from the Golang binary, I'm just going to also run GoReSim against that. So I think I just can get it from releases. And then we're just going to unzip this guy. All right, so we have it for Linux. So I'm going to put that on there. All right, and then we're going to do GoReSim on our Sliver binary here. So as you can see, it outputs like a whole bunch of different information that's definitely useful to us. So like already this package name looks pseudo-randomly generated. So this is probably related to the actual core functionality of Sliver. So I'm going to put that to a JSON file. Let's say GoReSim JSON. Okay, and then what we want to do next is actually import that into IDA. So there is an IDA Python plugin. So I'm just going to clone GoReSim as well. All right. So as you can see, we just recovered a whole bunch of different function names that we didn't have before. So like port, if I F5 this, I didn't mean to do that. So another thing about Golang is it's obviously statically linked, and then there's a bunch of conventions that can't be represented correctly, effectively in the hexarees decompiler. So because of that, you have a whole bunch of different things that can look weird or aren't represented properly or whatever. But for the most part, you can typically recover enough information using IDA's disassembler view and the decompiler view in order to reverse things effectively. So so I wonder why it's doing a jump out to these ASCII characters, if that's actually what it's doing. Oh, it didn't even disassemble these. Interesting. So we can force analysis, but yeah, these are just ASCII bytes. So maybe that's done on purpose. But yeah, these are just looking for genuine Intel strings. I think this is all Golang boilerplate stuff. Runtime argument stuff. But we probably want to look at some of these functions that were named with like kind of pseudo-random naming conventions. So let's just order this. So read at scalar unmarshal. I do also know if we can't get the debug information, we can do this another way too. So yeah, this is all pretty obfuscated. I think we can disable compile time obfuscation, at least for now, until we can get a better handle as to what some of these are doing. Let's take a look here. So we have shellcode encoders. Shikataganai, I think, is from the Metasploit framework originally. External builders. Oh, cool. You can create a exe, a shared library, a service. I'm assuming that just means like a server deal or a service DLL, or generate solely shellcode. That's pretty cool. Ret load, skip symbols. Okay, so yeah, that's what I wanted. -L. Let's get rid of this debug stuff. Okay. And that generated a lot faster, so I wonder how big this binary is. 11 megs, so it's still pretty big. But this should look nicer in IDA. And then I just always defang binaries as I go because I don't want the .exe, even though it's a binary we generated and we know what it's doing. But okay, and then I'm just gonna open this in IDA and in a separate window. IDA also indicates that a section is corrupted, so they might be doing more finagling. I wonder if the runtime obfuscation is only for these function names. So like if we look back at this one, then they could be or if it's all strings within the binary. I guess we'll find out. This might take a little bit to analyze. How y'all doing? All right. All right. While it's doing that, I am also going to install Havoc, so we can take a look at that as well. So I think we just need to go to the release page. I'll install this on my Kali box, and we need to install this Dead Snakes repo. Why not? We might not need it on. Do I have Python 10 out here already? All right, I think it should be okay. All right, let's see how our binary's doing. Okay, so we're done. So yeah, so it looks like these functions should be pretty straightforward. Obviously, having the plain text function names makes things easier, but we could probably apply what we learned to within this binary to our obfuscated binary. So we can start in the main here. Main. And we should have, okay, so main session startup. Okay, so we have a start connection loop. So setting up like transport connection channels and stuff. C2 implant, transport C2 generator. Nice. I can't even decompile that function. Oh yeah, I can. Never mind. All right, so C2 generator stuff. Runtime processors. Primarily interested in where they're storing that C2 domain, because that's information we would want as like analysts, right? So if we go back, session main loop. And this is probably going to be the command handler, register sliver. Okay, so this is interesting. So I'm not entirely sure what this is used for, but it looks like it's obfuscated strings. Okay, so get UUID, get OS version. So this is kind of all enumeration stuff that we probably want to reverse, right? Get process ID, get locale. Well, this one's valid. Looks related to the TLS negotiation stuff. So another giant pain with Golang is you'll often get these like giant string blocks, and I think it's another IDA plugin that's good for handling these. Oh no, I think these are actually separated already. Oh no, like these ones aren't, right? So you just have like basically these undelimited string blocks that aren't delineated properly, and then they're hard to utilize within the disassembly. Oh yeah, okay. So that's what these aren't. I think these are just undelineated strings. Sorry, I haven't looked at Golang for a while, so I kind of forget all the oddities that occur from it. So I do know that there's some more tools we can try to help with Golang. I think it's called Alpha Golang. So I'm just going to grab this guy too from Sentinel Labs. And I'm pretty sure these are just a series of scripts too. Do you want to remove these instructions? Sure. Let's see. So we go to Alpha Golang, that first script. Okay, there's a Golang identification. We already know this is Golang, so we don't need that. PCL, PC int tab. Or sorry, the PCLN table. When it's stripped from Golang, I don't think we needed to do that. So, did that just break stuff? I just italicized all my function names. All right, let's see what the other one does. Can I just, okay, what does function discovery and renaming do? Split full function discovery, function renaming, function pointer renaming. Okay, well, we definitely want that, so let's try it. Successfully created zero function pointers, that's okay. All right, I actually do really like this functionality if it actually works. It'll like categorize Golang functions into like little folders to make it more manageable. But again, I don't know if it's working on the current version of. Why didn't it work? Maybe I need to open the folders view. Whatever, we don't need that right now. The string cast stuff is actually what I wanted, which I think is going to help with those undelineated strings. Yeah, okay, cool. Let's try this. 6,000 suspected bad strings. Created 134 strings. Okay, that's pretty good. Let's go back to our main. We're going to synchronize with our text view here. Oh, interesting. It embeds the, obviously in the unobfuscated state. Let's get back to that enumeration function. But yeah, like as you can see, like even the number of parameters passed, it's like difficult to recover in IDA with Golang. There's just a bunch of stuff that's kind of a pain. Restart all listeners. Oh yeah, so I kind of wanted to pointer string URL, or that's library stuff. Because in the main registration function stuff, we should have we should have the initial contact that's established with the C2. Okay, so this gets a user identifier from the registry, it looks like, from the hardware config. So let's make note of that using last config. Pretty straightforward. It gets the OS version, probably using, yeah, RTL get version. And then it maps it to a string. So we have server 2012, etc. that's matched on by these values. So we go back up. And these are just string values. So cool. And we don't really need to rename these functions, obviously. What I do want to do though is see if it's a one-to-one code match with our other database. So to do that, I'm going to use bindiff. I'll show you what that looks like. So I'm going to save this database. So this is our plain text database, and then I'm going to use bindiff against that. So let's open our other database here. And I'm going to diff it against our obfuscated database to see if there's code similarities or if they're doing compile time obfuscation against the code itself. Because if it's just the strings, then that's not like a huge deal. But considering it's like many megabytes more, I suspect they're doing some compile time obfuscation as well. Obviously, we can just look at the source code. So we might resort to doing that, but it's kind of boring. So it's probably going to take a while just because it's a massive database. But it's an important step to do. In the meantime, I can continue with my Havoc installation like I keep saying I'm going to do. Too many windows open. All right. Let's add the Debian sources list to this. Do I really need to do that? It's all Python related. I should just be able to run this. Yeah, we don't really need 3.10. I just want to see if we can install this without that. Okay, we need to install the team server. Let's try and make the team server. Oh, I had to go back one. Let's see if it works. Pretty sure Havoc is, I think the team server is just written in Go. So we need to install those Go dependencies, but I don't think we need to, I'm pretty sure the implants themselves are written in C, but I'll double check. While that's installing, we can look at the agent. So what's kind of cool about Havoc is they have like a little GUI. So yeah, it doesn't really say. But if we go to the source code, cool. Yeah, we can mess around with this next too. Maybe we should have started with this because it's C instead of Golang. But so let's see what functions matched here. So there are a bunch of unmatched functions. So what bindiff does is it uses a series of algorithms to compare two IDA databases in this instance in order to determine what code overlap there is between the two databases. So the reason I wanted to do this with the plain text database and the obfuscated database was to see if there was compile time obfuscation being implemented in the at the code level, or if it was just doing string obfuscation. So for example, in this instance, we have these obfuscated function names on the left-hand side here, which is the obfuscated database that we were looking at earlier. And then we have the plain text functions on the right-hand side. And using a series of algorithms, bindiff has determined that these are like a 1.0 match, which basically just means that they're highly likely the same code. So and then what's cool about bindiff is, say I want to copy over this these function names, I can just right click and then go to import symbols and comments, and then it'll rename that in our database. So the reason this is significant is if we're in the wild and say we found an implant that was Sliver and we wanted to reverse it and it was obfuscated, we can use like this technique that I'm using right now to deobfuscate these function names and make it easier for us to read as analysts. So if I Command F on Sliver, then you can see there's like a whole bunch of these different functions that either are missing names or they are basically full matches. So I'm just going to select a bunch of these all at once. And then as you can see, the algorithms have like effectively deemed these as having lower similarity. And then the lower similarity that you have, the more different the colors are. So you have like bright green, and then as the similarity and confidence gets lower, then it goes to yellow, and eventually like orange, and then red. So pretty nice. You have like visual indicators that can be used for you to kind of do things quickly. So if I select all of these and then do import symbols and comments, so obviously you want to be pretty careful about what functions you're copying over. So if we like order by similarity and confidence, then we can basically only copy over things that are high similarity. So if we look at like this, for example, okay, so there's like a bunch of like, okay, so I'm actually gonna go back, because see how some of these have low confidence, but they have high similarity. I basically only want to copy over the ones that have a high level of both. So I'm just going to copy these. And let me know if you have any questions, if you're like, why is he doing this? Or let me know if we should look at something else. Okay, so I copied those over. And kind of as mentioned earlier, there's some of these that are quite different. So you can actually double click on one of these entries, and then on the right hand side it'll navigate to which function differs here. So as you can see, these specific functions probably have low impact on the functionality just because they're like these move operations, they're probably related to pointers. But like is valid go lang, like there's a bunch of these that or is valid go that are gonna have low impact on our reversing, right? And then they have low confidence levels, so we don't really want to copy over the names. Okay, so what I was going to mention as well is if we scroll down here, we can see that there's a bunch of these sliver functions that were in our other binary that are effectively not present in this one. And we can look at like primary unmatched here, and we can see the same thing. So there's a bunch of these these function names that were not present in the other database. So what that tells me is that there's probably some kind of compile time obfuscation here that's been integrated in the Golang code that is changing those function signatures, but it wasn't for some of them. So if we go back here and then search Sliver, we can take a look at ones that were indeed similar. And again, these might have low impact, so the quote-unquote important functions that we need to reverse might not have been found in this instance. Register extension. Yeah, so I suspect that even though these had high confidence matches, these are very like generic functions. They don't really have a whole lot of code. Or this one does, actually. So I might take that back. But they mostly look like setup functions for some of the functionality. So yeah, I do suspect there's compile time obfuscation in the code itself. So if we look at that code that I downloaded on our Kali machine, then we can see what that looks like. Okay. So let's look at the, I don't really need to look at the implant code. I'd rather look at the builder and see exactly what this looks like. Oh, it needs to install it on the Kali box. Okay. So if we go back to the source code view here, we should be able to see the obfuscation steps that are taken. So as I mentioned earlier, like Go is highly readable. Like this is pretty straightforward to read. So like the stuff that I care about, right, from a Blue Team perspective is like their ability to generate these different types of payloads. So for example, if they call generate sliver executable, and we go to the definition, we should be able to get an idea as to what the build process is like. So if we go to render sliver Go code, that's probably a good place to start. And then it looks like they're passing some Go build stuff to go build, which I believe is a library. Yeah, it looks like the standard library for Go. So I just want to confirm that. Go build. Yeah. Builds reproducible binaries for modules. Sorry, that's probably tiny for you guys. Go build builds reproducible binary for modules available with the Go proxy on demand. So that's pretty cool. It's highly convenient. So then if we look at the render sliver Go code function here, then we can see there's a build ID that's passed. There's an implant config that's passed. There's a Go config that's passed. And then there's an HTTP C2 implant config that's passed. So a bunch of different parameters. And then we have a randomize implant config parameter call that's made in this models area here. So this is probably actually in the models package. So this is probably very important. So I'm just going to make some notes here. I'm just going to open my notes from earlier that I closed because I needed to SSH. Sorry, 2 seconds. All right. All right, so a few things to make note of thus far is that we have compile time, obfuscation, effects, both function name strings and code itself. This was confirmed through generating one obfuscated binary and one non-obfuscated binary. Runtime check-in generates, makes use of hardwired identifier from the registry, whatever. We don't really need to write out all this stuff, but the registry, etc. But we do have the HTTP C2 Go file that contains the models package that we do want to look at, right? So let's see what else we got here. So if we look at the source code and go back to the randomize implant config, we could probably see what they're doing to actually randomize it. Okay, so it looks like generates a new implant config from the parent config. This is the primary configuration used by the implant generation. And then is it just using generate random path segments and generate user agent? Is that the random part? Because this is a struct here. Okay, and they're using protobus as well. So this might be a pain in reverse. But yeah, from what I understand, protobus are a custom format that was developed by Google, so it makes a lot of sense because it provides a lot of flexibility with Golang. But are they just outputting that in JSON format? I think so. Okay, that's straightforward. But what do they do with the config? Like, where do they store it? So once they randomize it, I still don't really see how it's randomized. Okay, where's this guy used? So we have directories, go path directories. Mostly just want to see where this config's used. We have encoders. Okay, so slivercode.execute, implant build, config, build C2 plant, or PB. So that's what was, so I suspect they probably have multiple different methods that are used to store the config. But I just want to confirm that this is what we got from, okay, so this is what we were just, okay, so it generates like all the build paths that it needs and joins them into a Sliver code path variable. Then it creates that directory. Then it has a Sliver code raw variable that's written. So I'm assuming that's just the unmodified one. So what's this encoder list for? Okay, so it passes that encoder list to this execute function as well. Let's see. Okay, cool. So like pretty straightforward. And then we just have this canary domains generator thing. So that would have been executed with our code earlier. Cool. Okay, so let's look at that execute directory that we were just looking at. Or not, sorry, execute function, t.execute. So let's look at that execute directory that we were just looking at. So it's executing the template. There's a bunch of Golang stuff that I'm not super familiar with, so we'll see how this goes. Define templates. Oh, this is in the Go standard library, so we don't really want to look at this. Buff. What's this buff? Oh, cool. Okay, so it's a template. And oh man. Okay. Yeah, it's more complicated than I thought it was gonna be. All right, let's see. What else do we need for Havoc? Because I also wanted to take a look at that today too. Those instructions, installation. Okay, then we can just do make client build. And then we should be able to do just run the client as well. So let's add to our notes. So build pipeline makes use of Golang templates to template custom configuration information. And we're going to figure out exactly how that works. And then let's see. Okay, Havoc's building. How's everybody doing? All right, while that's building, I might run to the washroom real quick. So I will be right back. All right. Glad to see this build didn't do anything while I was gone. All right, let's see. What else we can do? Maybe this thing's like running out of memory. I don't know how much this Kali image has. How y'all doing? You're quiet. Bored? This is boring. Learning how all these frameworks work. Nice. I love burritos. All right, let's see if we can continue looking at that Golang code from here. All right. So then we got the main enumeration. Obviously the operating system type they would want. Okay, so it looks like they're creating this struct. So I'm going to do create new struct type. Oh, that looks gross. So if I want to make the offsets readable, these are 64-bit integers. Reconnect interval. All right, I might try. I thought Alpha Golang would recreate those strings, but it's not. So extract types. Maybe I'll try this type one too. All right, let's give it a shot. All right, looks like it found some stuff. That's cool. All right, we still want to find the config here, so I'll focus on that. The template. So these are the structures. These are all the models, right? Yeah. I like they have a burned field for their implants. Implant config struct. Okay. That's what we were looking at earlier. Okay, so it converts it into a protobuf. Okay. Save implant profile. Oh, this is just when we're saving it. Okay, server generate. This looks good. Save implant profile. Oh, this is just saving it to disk. But maybe we want to look on the server side. Okay, it should be under generate binaries. This is what we were looking at earlier. And the final step was that okay, so it's probably written into a Go mod file. Let's see what that is. Okay, it's just a specific module file. Yeah, okay, that's fine. Okay, so yeah, it must be applying the configuration. What's driving me nuts though is like there should just be a straightforward area that the C2 config is applied to, so that's all I'm trying to find. There's so many dependencies for this. I know we're just looking at this, so. Okay, once it generates a package path. Okay, so that's how the flags differentiate. So if we go to like, a different type of executable, so like Sliver shared library, then we get a extension that's picked, and then they'll use these different link parameters based on what it's doing, or based on what operating system it's compiling for. So that's cool. Template function map. Okay, so it's literally reading the code from file, and then it just modifies it based on a template. So we should be able to read the actual implant Golang code and then determine where the config is read from, and then work backwards from there. Let's check on how our compilation is doing on our Kali box. Okay, cool. It looks like it worked. Let's see if we can execute Havoc. All right. This is super tiny though. I wonder if I can make this resolution any higher. That should be good. All right, new client. Let's see, attack, payload. Okay, so let's make a daemon agent. Sleep technique, sleep jump gadget, proxy loading. This is pretty cool. There's a AMC ETW patching. Let's just do Win32 injection for now. And then it's going to inject into notepad.exe. All right, let's build it. No specified listener. Okay, let's start a listener, and we'll just do HTTPS. And then let's generate a payload again. It's cool how it has all these options. All right, let's do Win32 again. We'll leave out the AMC patching for now, but I am curious how it does that. All right. I don't know how long this is going to take to build, but let's also open that. Open Havoc. Visual Studio Code really loves to tell me that there's updates. Okay, let's look at daemon. I think I think once it builds, we can actually just look at this. So, and it's done building. All right. So let's make a little directory for Havoc, and then let's copy that over. Our daemon malware. I'm gonna open that in IDA, and this should be easier to analyze, but maybe not. All right. At least it doesn't have 22,000 functions and isn't 10 megabytes. I bet this thing's tiny. 100K. So let's look at the imports here. Okay, so imports are dynamically resolved. Makes sense. These are probably hashes. And these are probably function tables. And this is probably also function hashing resolution. Oh yeah, it's straight C. Let's install the C extension. So I don't really want to cheat with this one because I think we can actually reverse this pretty easily compared to the Golang stuff. I shouldn't say pretty easily. I'm gonna eat my words, but at least it's not 22,000 functions. But yeah, if we look at like, so typically where I would start off in a binary is seeing like, okay, is there any imports? So there's no imports here, which kind of makes sense if this is an implant that's going to be injected. If we look at the, actually, I will also submit this to assembly line because I'm curious. I'm probably logged out now. I don't know what's up with my AL instance. Oh, there we go. Just took a little bit. Is this thing healthy? Yeah. All right, let's submit that Havoc sample. Okay, I'm going to submit that and see what happens. So yeah, when I initially open a binary, in addition to submitting it to assembly line, which I don't know why it's not uploading, but I'll look at the imports, say like, okay, there's no imports, so that's pretty interesting. Open strings, not a whole lot of strings either, also interesting. So this binary is obviously trying to like hide stuff, right? Because in a normal executable, you'd normally see strings, imports, external libraries being referenced, etc. So right off the bat, pretty indicative that this is malware if you were triaging it. But if we go back to the start function here, let's figure out what these runtime resolved hashes are, or what I believe to be runtime resolved hashes. So we can do a few things. I think I have, let's just see, I think this is an executable, but I'm just gonna double check. P64, yeah, it's a GUI application. Okay, so I'm just gonna open this in x64 debug. And let's dynamically resolve those functions, if that is indeed what that's doing. So I have this open in my other IDA window, so let's see if I can switch back and forth easily. So I'm just going to put this in a different space. There we go. All right, so let's go to this function. Right, this is probably mapped to a different address because it's probably has a dynamic base. And shout out to Duncan, we have a bunch of Easter icons because it's Easter weekend. That's really funny. All right, let's see where this is mapped at. So let's rebase our IDA database to this. I'm also going to take a snapshot. Hey, Matt Depp, are you still here? Did you see how they're embedding those canary domains? Did you see any of the stuff with the canaries? No worries if you're working on other things. I see it gets added to the config, but I'm not seeing where it gets added to the binary. Yeah, same. It's annoying. So I'm pretty sure they're just like literally generating source code on the fly. Actually, since I have, okay, don't let me get distracted. I'm going to do this stuff with Havoc first, and then I'll go back. But like they should have, I'm guessing, like they're generating those Golang directories on the fly, but they might be cleaning it up afterwards. But yeah, let me just finish what I started here, because otherwise it'll be too much back and forth stuff. Okay, so let's rebase. So I'm just going to rebase my IDA database to this address. All right. So he's using this straight offset from the thread environment block. And then this value passed to this function. All right, let's ignore that for now. Yeah, so this is a dynamic function resolution. So we can just let it map. We can just let it generate this function table here, and then we can dump the binary. So, well, let's take a look at what that actually looks like. So basically they're passing 2 arguments to this function. The first is probably the DLL name, and then a hash for function resolution. So if we look at the offsets here, so this would be the image header. All right, I don't know why these aren't lining up properly, but we don't have to worry about that right now. But what this is doing is it's walking the it's essentially dynamically resolving each of these functions using hashes. So if we look at the second argument for this, so this will be the hash, then this will be the image base of the provided image. And then essentially this is getting the export directory for a portable executable in memory and a DLL portable executable in memory. And then basically it hashes each entry within that export header. Sorry, within that export directory, not the export header, to resolve a particular function hash. So if we look at this, this is actually the hashing function. So I don't know if this differs across multiple versions of Havoc, but this is the hashing function. So let's mark that. And then this looks like a string length function. Or is this just incrementing? If A1 is equal to I. Okay. That's not string length, but that's okay. And then it looks like it's called, so this might be like get proc address or something. But let's step through this and then just see exactly what that looks like. So let me pull that up. Hey, all friends, how's it going? All right, so if we step into one of these calls, we will see that this is the hash value, and then rax is going to be the offset to the image file header that I was attempting to resolve in IDA, and then that's going to be added to the base pointer, and then this is essentially the RCX currently has the first export within NTDLL, which is the DLL that they're using to access the exports for. And then if we go to our IDA window here, then they're going to be calling the function hash, which is this B5EE090. So this is the function hash function right here. So if we step into that, we can just see it hashing in real time. So it's basically going to take each character within that A SHA-1 or A SHA final export, and then it's going to just conduct these hashing operations. So it's just doing a sub and then IMUL on those hashes. So again, if this isn't modified at compile time, then we could hunt on these hashes. So obviously this isn't the function that they're looking for, but if we re-implemented that hashing function, which is essentially what hashdb does, then we could look up those functions within hashdb and then map those to known function strings. So I'm just going to let this hash, and then so it's resolving loader load DLL. Let's go back to our IDA here. So if we look at what happens is this global variable is being passed into multiple local variables here. So I suspect this is probably a resolve function table. And then we have these functions that are being that are also referenced in this table. So I'm curious what these are for, but so let's go back. Basically, I'm just going to let this resolve itself by letting it run in the debugger. And then we should have a full function table after this. And then you can see here that each function resolution result, which was what I was trying to explain earlier, is moved into a respective offset to this struct. So we can actually create new struct type. And then we'll have each respective function that's accessed at each respective offset within this structure. So instead of like stepping through and doing this all by hand, we can actually have the debugger do this for us. So I'll go back here and let these all resolve. And then we should have a bunch of function pointers. So if I go back, this global pointer, if I copy this, we don't want the keyword in front. Was it modifying them? I was expecting these to be valid function pointers. Hold up. So let me, I'm just going to restore that snapshot. How's everyone doing? All right, let's see what it says. Looks like they're not modifying the timestamp at build time. Kappa returned a bunch of results. So encrypted data using AES, so that's interesting. We could probably apply Kappa against this too. So it looks like the hash might be standard DJB2. And then Yara, Yara didn't really provide a whole lot. Interesting. Okay. So yeah, probably worth looking at Kappa to help us reverse this. When you ran strings on the binary, you didn't find the domain, right? No, I didn't find it. Because I just put invoke, like some test invoke domain as a string. So I'm reading the docs and it says it wants the FQDN trailing period. Oh yeah, that could be why. Nice observation. Yeah, I can generate another Sliver binary. That's no problem. All right, let's see. So yeah, I just want to walk through this again and see what is being done with the hash after it's resolved. Loader get procedure address. Okay, so I think there's just not a symbol at that particular address, but it is resolving them. So we probably actually do want to use something like hashdb. So I know I have hashdb in Binja. So instead of messing around with the IDA Python installation I have, I might just do it in Binja. Hopefully this isn't hashdb. Yeah. Roll 9 add ASN1 boolean. Yeah, that's just like a test function. Oh, there's a bunch. Well, there's a variant of DJB2, so let's try that because I think we had Kappa identify that it was DJB2. All right, much better. I like malware analysis. Can I stay? Yeah, for sure. This is primarily malware analysis. We're just looking at red team tools today. So what type of exe file are you analyzing? So this is from the Havoc C2 framework. Are you familiar with Pegasus spyware? I haven't looked at Pegasus myself, to be honest. So I'm not entirely sure. Yeah, I don't really have a lot of familiarity with iOS stuff in general, but I think that'd be cool to look at. All right, sorry, let me create the structure. Let's just call it, we can adjust the size later. And then I'll just make RDI. I know there's a way to, it's because they're new local variables every time. Yeah, I think so. That's probably why I can't do it automatically. And these offsets are, okay, so we should be able to make this into a structure. That's annoying. All right, well, maybe what we can do is just resolve all these and then I'll create the structure after. But yeah, it's gonna be kind of a pain. So what I'm doing here is basically HashDB has downloaded all the hashes for that particular algorithm for this particular DLL, which is NTDLL. Oh no, sorry, not NTDLL. These are all part of, I think load DLL is NTDLL, but these are, what? Maybe it is NTDLL. Anyways, it doesn't really matter. But basically I'm just resolving each hash using the hashes that were downloaded from HashDB. So all of these were stored in a enum automatically by HashDB, and then those are available on the left-hand side here. So I'm just basically applying the enum members to each respective hash. This is what I was trying to do dynamically, but because there wasn't a label for each respective offset, it was a little bit harder. So this is a lot easier. So basically these are all the functions that the malware is going to use at runtime. And then it's going to be storing them in this global variable. Okay, so this might be a new one. Maybe can't find that. All right. We'll worry about that later. Yeah, these are all NTDLL functions. NT open process, NT terminate process. And then once these are resolved, we can create a custom structure that we can apply to that global variable. And then, so like if I select this global variable, should see our cross references here. You can see that like all those offsets are used throughout the binary. So this is basically a function table. So basically we need to do this in order to understand exactly what's happening in the binary. All right, so let's see if we can hunt these. I'm assuming it's the same algorithm. Yeah. So just make sure that one's set. And then we'll just search for these. Okay, so these are kernel 32 functions. So is this a different? No, it's the same hash table offset. Okay, cool. So if we kept looking in that like dynamic method I was using earlier, we would have seen symbols for these functions later on. So like if we look down here, okay, yeah, so there's some Boolean check here. that might prevent the resolution of kernel 32 DLL functions. That's okay. I wish there was a way to batch these, but you can only do it with HashDB when they're sequential and like basically a hash table. So the fact that they're all kind of inlined like this is a pain in the ass, but we'll get there. And then I have an idea for constructing the struct so we don't have to do it by hand. All right. So I'm going to copy out the pseudocode and I'm just going to parse this with, I guess we could script it. Maybe we could script it. Because we can walk all this code with binge scripting. Like, is this considered a basic block? Because that'd be really useful. Yeah, cool. So let's do the first basic block. 40. Oh, the HLIL basic blocks probably. 11 to 190, is that what we want? Cool. And then I've never parsed the basic blocks, so let's see. There's no like instructions. Just instruction count. All right, I'm just gonna use, they did release a new version, so I might have to restart after I updated it this morning. All functions, are you alive? Okay. All right, cool. Structure for me. All of the Windows function names. Let's see what the models can do for us. Weird. I got the first one, but not the. Hold on, I gotta restart. So it turns out last stream when I was messing around with this, it's basically said, or like those errors I was getting was my fault. So, because I basically updated the client. There was a client mismatch basically between the Sidekick server and mine. I could just mark up everything in IDA that I resolved externally, but that's pretty gross. Oh, friends, have you messed around with Sidekick at all? I'm a Geezer enjoyer. Yeah, Geezer's pretty awesome. Did you use Geezer for the course, or did you use IDA? Only Geezer. Nice. I'm currently rewriting it for people to use Binja, which should help because the free version has the high-level IL decompiler, so it should be a lot easier. Maybe we can even do a Geezer edition at some point. I also wanted to try and get people used to looking at assembly rather than just the decompilation, because like stuff like this is pretty good, but like you saw with the Golang stuff, or well, no, Golang's not a good example either because there's like a million instructions, but sometimes the decompiler fails and then you need to read it. I tried to use IDA-free in the past. Yeah. But the stuff in the course is at least simple enough that you should just be able to use the disassembly. Okay, so I can get, so let me open up a snippet here. I'm just gonna make sure this works. Nice, that's cool. I have some friends that like don't even use F5 ever in IDA. Alex, but he's pretty elite, so Okay, so I should be able to just identify these patterns. So let's do like current, and then get param, not parent. Do we have function? No. That goes back up. All right, there we go. Oops. All right, let's try this. List object. It's not attribute operands. Instruction dot. Instructions, a list object. Maybe there's different types. Let's do it this way. Okay. I don't know what these are though. Constant string pointers. So if I do like, I just want to make sure that it's the correct call. Whatever, we can just do address. Variable object, no address. All right. Let me see. Instead of struggling with the object names, blah, blah, whatever, we can just ask the model to do it. There we go. It's just one of those days today where everything takes forever and everything's annoying. Alright, let's just do this whole thing. I think the LLM's lying to us. I really just need like a bunch of boilerplate techniques for this sort of stuff. Name. Unreal. All right. Let's change gears here because this is getting really boring. So, okay, so there's a bunch of stuff we can do. I will sort out the function table resolution stuff. Probably for next stream. Then we can fully RE Havoc from like a defender perspective. And then I do still want to look at how the C2 information is embedded in Sliver. So why don't we do that for a little bit longer? We've been going for 4 hours. So yeah, let's take a little bit look. Let's take another look at Sliver, and we'll kind of summarize our notes here, and then we'll kind of have a better idea of what we want to work on next stream. So all the source code is there. Like, it's not really like it's crazy difficult to compare the two. So it's kind of the point I wanted to get across at the start of stream. But we should probably see what we can get out of Sliver, and then I'll sort out the function resolution stuff for next stream, have all the markups done so you guys don't have to watch me do it boringly now, and then we'll go from there. But yeah, there will be another stream on this just because we're kind of just getting our footing here today. So let's take a look at what it does at runtime, what the implant does at runtime. So we should be able to work backwards from there. Drivers. Nice. All right, I'm just gonna keep looking through this stuff. Update vendors, Sliver. Okay, here we go. Locale, Okay, so it can create services. The screenshot technique uses an external screenshot Golang package. I'm assuming this is process stuff. Yeah. Man, this is super extensive. Oh, nice. Thanks, Matt. Dip. I'll add that to our notes. So in, okay, so we probably want to look in generate.go for the other stuff, right? Generate.go. Cool, okay, this looks good. Verify that first. Canary domain, range split, ensure FQDN. Okay, so that's probably why I did not embed my test one. Yeah, that makes sense. Canary domains. Yeah, this is where it's initializing that template. Cool. And then where does it use this? Yeah, parse compile flags. And it has C2s in here too. Generate beacon.go. I think the beacon is just the stager, so we don't really want to look at that. Okay, profile's new. Save implant profile. This is protobuf stuff. Context background. Yeah, it is. I just don't know. Yeah, I think it's both. I think it's the right place for both. But then it's save implant profile is where I'm kind of getting lost here. Okay, this looks like where it's used, which is where it's actually used. So it's saving the profile to disk. And then in a protobuf. So we should be able to find where it's reading the config from the protobuf and then embed it in the binary. Oh, cool. There's a backdoor command. So you can backdoor existing binaries. More stuff to look at. I think this is all server-side stuff. Maybe I can look for that. There's got to be, in that build, there just has to be. Or sorry, generate. Like I'm assuming it's templating out the Golang and then it's going to be generated there. Let's see if, okay, here it is. So it's in, that's okay. So like, okay, I think what's happening is it creates a protobuf, it writes it to disk, and then during the build process, it like reads that protobuf from disk, and then generates like Golang code on the fly, or like it uses the template with the embedded C2 config, and then that all gets inserted into the final binary while it builds it, if that makes sense. So I think the reason it's just confusing is because there's like a protobuf step where it's like writing the config template to disk with like actual Golang code, and then it builds it into a final binary. So I think that's why it's just confusing for us. But I know people who work on Sliver, so I can literally ask them, but I just kind of wanted to figure it out for ourselves. But yeah, so this is where it's stored in the plain text version. But obviously threat actors aren't going to use the plain text version, so but at least we know it's in C2 generator, so in transports, in the final binary at least. Maybe I'll just go navigate there myself. transports HTTP client. C2 generator. Maybe if I just search C2 generator, begin session transports. Here we go. Yeah, so any C2 servers that are defined will override what is configured in the implant. Okay, so here it is. Mad dep. Man, what a pain in the ass. I'm also not very well versed in Golang in general, so this is probably like a skill issue on my part. But let's link like directly in the code where this is config.debug. Okay, cool. Oh, I see. Okay, so it's not being overridden. Okay, so it's just saying that it'll have updates later, I think. Random domain C2 servers. Okay, I think what I just said was incorrect earlier too, where yeah, there's got to be an area that this is happening, like this is being embedded. So value.url, maybe that's what's being overwritten here. Let's see, being referenced elsewhere. I don't see anything about the canary domains in that file. Yeah, sorry, I was just talking about the original C2 domain. The canaries are probably embedded elsewhere. But let me generate, oh yeah, I think I have to start the Sliver server. Okay, so I think I just have to restart the Sliver server. Okay, it's up now. So I'll do generate canary, then I'll just do canary dot. Oh shit, do we want to, we don't want to disable canary. And what was the, is it -L? Okay, let's try that. You need to enable the symbol obfuscation, I think. Yeah, that's what I was just trying to fix. Weird. I wonder why, like maybe it means canary in memory? I'm pretty sure I'm doing it right. Let me try opening it in IDA. Am I crazy? Oh, is it Sliver? That's why. Start a DNS listener first, maybe. But it's embedding the like C2 domain correctly. But yeah, I'll give it a try. Right. Both your canary domain, yeah. I'm just gonna copy this over. Nothing. It could also be check your name again. Did it end with 2? Not the domain name. Yeah, oh, it's because, sorry, I'm confusing you because I SCP'd it. Like I SSH copied it to my machine. And then I just named it something new. Sorry about that. So this could be non-ASCII. So I'm just gonna open it in IDA to like triple check. So we want Sliver. All right, so while it's going, let's write a few more notes here. So in plain text binary, the C2 is embedded in this function. And then we got the canary stuff that you mentioned. And then C2 profiles are written to a protobuf in client generate and read during build time while being embedded in raw Golang code by build system. Canaries do not appear to be in plain text when embedded properly. What else? So we'll say Havoc uses DJ2. Was it DJ2 hashing function? Of course, I got signed out. I should be able to check and hold on. DJB2 resolution upon execution. To do finish dynamic resolution resolution code and markup IDB for next stream or BNDB. Okay. Then finish reversing Havoc. We can also add a to-do here. We'll just do find where domain is used in obfuscated sample. Okay. So I can do a quick check though. So like this function is a part of this interface, which is used here. Does it have more than one reference in that? Because it should have in some like initialization stuff. So get client, C2 generator. This is like stuff we want to look for, right? It's like this interface. So if we have like, because identifying this particular interface is what's difficult, right? I think I just heard the other IDB bong, which means it's done. So if we go to strings, the first strings table it's going to make is going to be ASCII probably. But if I go to setup and then I'm going to enable all these different types of strings, I think Unicode should cover what I mentioned. But we should be able to look at the Golang data type, right? Generate beacon, for example, canary. So it's looking for the string canary in the raw code, and it's embedding it there. So what I want to know is where it's writing that raw code. Oh no, sorry, that's getting the command line arguments. Command flags get string, sorry. Split on raw canaries. Like it's just a string object, right? So it's not UTF-8 is what I was looking for, so. But let's see. Yeah, weird. I'll probably look into that a little bit closer as well. All right, so we got some stuff lined up for next stream. I know we didn't get as far as I would have hoped, obviously, but I think we made some good progress. One last thing I wanted to check was if you can like pivot off of one of these interface functions. So I should be able to like look for this example in our diff examples, or if in our diff results from earlier. So if we have this guy, all right, hold on. Wow, I really wish it would stop doing that. No, these are different. So like, if it's within its own interface function, I don't know. I'm gonna brainstorm some ways that we could probably find that C2. But one last thing I want to do is submit one of these Sliver binaries to a third party to see if we can get some stuff. And I was going to use assembly line to do that. So I'm sure most of you have heard of Triage, but it's a pretty awesome sandbox. And they're now owned by Recorded Future. But basically, I'm going to submit this to Triage using assembly line. So I just kind of want to see what happens. So I know a lot of these services do have coverage for Sliver. So very interested to see what we see. So it's just waiting on Triage. Thoughts on uploading red team tools to public sandbox. I don't know. I think it's fine. Like these are all open source, right? So it's like not really a big deal. I guess if you were like paying for a commercial red team tool, then you probably wouldn't want to upload it to public sandboxes because then people can get the payloads. But since this is like a free and open source tool, I don't think it's a big deal. What did you have in mind, ill friends? Me nothing. There's a debate on Twitter. Oh. Fair game in like what manner? Oh, it's hit a Yarsig. Yeah. Not this Udkonos one. I think this might be I might have to disable this. Because this hit on something else last stream on that 4px sample. It's taking its sweet time. All right, while this is going, I'm just going to run a quick ad. So for those of you who are interested in learning how to reverse engineer malware, like Franz, who's on stream, finished the course, etc., we have a malware analysis course that you can check out. It just helps us support the stream and tooling and stuff that we're doing. So you can check it out here. I'll link it. It's called Introduction to Malware Binary Triage. And, oh, they're finished. Look at that. You can check it out there. And I'm just going to run a quick ad for it. And I'll be back in 2 minutes. Hey everyone, my name is Joshua Reynolds, and welcome to the Invoke RE Introduction to Malware Binary Triage course. Throughout this course, you will learn to triage and reverse engineer malware binaries using a number of proven techniques. These include static analysis, which is the concept of analyzing malware at rest, and dynamic analysis, which is the concept of analyzing malware as it executes. We will also be analyzing network protocols used in malware command and control communications, malware obfuscation, packers and how to unpack them, process injection, how to write effective YAR rules to detect malware variants, and how to compare malware samples at a binary level. This course consists of 11 modules, each containing lectures and practical labs to apply knowledge that you have gained as you complete the course. We provide both video and written materials, so no matter what your learning style is, you can complete the course successfully. Thank you for checking out the course, and we look forward to teaching you. Cool. So it looks like this aired out, so it did not work. I'll look into exactly why this happened, but it's just not our day today. So Johnny Sins cameo, yeah, totally. Yeah, Sergey's like meme commercials are definitely a lot better than mine. But cool. Well, thanks for tuning in. Oh, here, actually, one more thing I'm gonna do is link our Discord. Again, I really need to set up a Discord bot, but so I'm just hopping on here. So if you want to check out our Discord, you can join here. Yeah, thanks, Matt Depp. I appreciate your help. Hopefully we can make some good progress and then mess around with more stuff next stream. So I'll have a better idea. I kind of walked into this just being like, okay, we'll see how these are set up. I didn't really do too much prep, primarily just because I've been swamped with everything lately. But I think next stream we've kind of established a good footing and foundation of how some of these tools work. And then I'll have a better idea of what we can accomplish next stream. So, but yeah, I appreciate all your help. But yeah, if you want to join our Discord, you can join there using that link. And I'll see y'all later. Have a great rest of your weekend. Take care.